In this video clip, we will discuss how noise is measured in terms of various parameters. The very first and one of the most famous ways to measure noise is in the form of signal to noise ratio. So let us define what exactly is this. In the communication systems, the comparison of signal power with the noise power at the same point is important to ensure that the noise at that point is not very large. And hence we define a ratio of signal power and the noise power, which is given as S upon N. So S upon N is nothing but S here is the signal power, which can also be written as PS, and N is nothing but the noise power, which can be written as Pn. So this is the signal power. When I say signal power, it is the power of the signal which is of interest, which is the information signal, with in simple words, the signal which must be present in the communication system at that particular point. Pn is the noise power. It is due to the noise signal. No doubt that noise is also can be called as a signal, but noise is that signal which is not of interest, which is present there due to some other reasons. It is not the signal which contains the information, and hence we call it the noise power. It becomes the power which is represented by the unwanted signal in the communication system. So the ratio of the two is called signal to noise ratio. Now it is very obvious that ideally noise power should be equal to 0 and ideally signal power should be infinity, and hence we can say that ideally signal to noise ratio should be infinity, but in any practical application noise power can never be 0. Any device or any component at room temperature will generate the noise power. We have discussed that before. This noise could be simply due to the thermal noise source, and hence it is not possible to have any component or device with noise power being equal to 0. We can only make noise power as small as possible. So practically SNR should be as large as possible. That ensures that the noise is less compared to the signal of interest. In many application, SNR, which can simply be written as SNR PS by PN, is measured in dB. SNR in dB. That is simply because signal power could be very large compared to noise power in many cases. So PS by PN can turn out to be a large ratio whenever we have large numbers appearing, and especially when we want to plot or when we want to study SNR over a large frequency range. It becomes very important that we measure or we represent it in dB scale. Whenever you take the ratio of 2 power, the formula of the dB value is nothing but 10 log PS by PN to the base 10. So this is how we will represent SNR in dB. Going a step ahead, I can represent signal power as Vs square by R, the signal voltage that is being dropped across the resistance at that particular point, and noise PN, noise power due to the same resistance R, can be written as Vn square by R, where Vn is the noise voltage. Now we have used notation En in one of the previous video clips. Please note that Vn and En are exactly same. So if I take the ratio, SNR will be nothing but Vs square by En square, because R will cancel out. It's a common resistance that we have taken as of now. And if you now represent SNR in dB, then it will be 10 log to the base 10 Vs square upon En square. Because it's log of something squared, that 2 can be taken out and it will become 20 log of Vs by En. So whenever we take ratio of voltages, we have to multiply by 20, and whenever we take ratio of power, we have to multiply by 10 to get the dB value. So SNR in dB can finally be expressed either using this expression, or we never find the voltage values and express the SNR. We always directly obtain power value. So this is the most famous expression that we use for SNR in dB.